Hi, I'm Derek. My team members are Devin, Vartica, and Ritwick, and this is our capstone project, Causal Inference in Complex Systems using Omega for the graduate course Causal Modeling in Machine Learning, taught by Dr. Robert Osazuwa Ness at Northeastern University, Khoury College of Computer Science. We're looking to implement a version of the Lokta-Volterra equations using Gillespie simulation, and we'll be using this with the probabilistic programming language Omega. What this will allow us to do is to reason causally about our system and be able to ask various counterfactual and interventional questions about our model. And so we want to answer, can causal modeling be applied to complex systems? Complex systems can show up in lots of different domains, from biochemical systems such as cells to environmental and climate systems and economics. And so if causal modeling is able to be applied to these complex systems, we could answer counterfactual questions. However, complex systems are difficult to model due to feedback loops, nonlinearities, and time components. Directed causal graphical models such as SEMs implicitly assume a stochastic dynamic system has reached some stationary equilibrium state, but many dynamic systems are non-stationary. So we'd like to model them explicitly as stochastic processes while still reasoning about them in the same way we would with interventions and counterfactuals in directed causal graphical models. So previously, there had been extensive work in using SEMs to model biochemical systems. This process involved essentially simulating a system out to equilibrium and then being able to model the relationships of the various variables that we're working with into a causal DAG with the corresponding functional assignments. You're able to answer causal questions about the system. You can learn the functional parameters from data, but it essentially shrinks the complexity of what kind of model we're capable of and what kind of causal queries we're actually able to ask. So we are restricted to a DAG. And so what we also removed from having to simulate to equilibrium is the time component. And so once we have that steady state, we can reason in that steady state. But what if we wanted to ask certain causal queries about what happens if I intervene at this variable at time t equals 10, and then see how the rest of the simulation is able to play out with that intervention at that time period. And so SCMs just inherently can't capture this complexity. So what we're attempting to do is to essentially overcome some of these restrictions from using an SCM and instead looking to use probabilistic programming to actually model this dynamic complexity. What probabilistic program allows us to do is these time and cycle components of systems that have had to get cut out of SCMs, we can actually implement using recursion and dynamically determined interventions, which an example would be, say we want to intervene when a certain value reaches a threshold of a certain value, and we can look at that throughout time, and we can actually intervene once it's able to hit that threshold. So we can ask a lot more interesting and innovative types of interventions to make counterfactuals. And so what we're going to be doing is we're using the library Omega in Julia, which is a probabilistic programming language. And in theory, once this program is implemented, we can scale it to any system that is described by a set of stochastic or ordinary differential equations. So Omega is a causal probabilistic programming language that's implemented in Julia, and it essentially allows us to construct these generative causal reasoning models dynamically. And we can build more complexity into the model, and with that we can perform more complex counterfactual queries, and it was developed by the authors you see on the screen. Omega is designed to support first conditioning on predicates, and so how it actually does this is through relaxing the constraints of predicates and making them soft predicates. So for example, say we wanted to condition when x equals y, how Omega will actually run is it'll attempt to answer how close are x and y, essentially through calculating the distance between x and y and then running that through a kernel that ensures that the value we get is between 0 and 1. And so it allows these soft predicates to actually get conditioned on. And then it also conditions on distributional properties, data generating process, and then finally causal inference. We can actually reason about complex causal systems. We're not restricted to just a causal DAG. We can actually build more complexity and answer causal queries using probabilistic programming here with Omega. Essentially, it accomplishes this in part by creating two new types of objects in Julia. We have the Omega object and then the randvar object. And then in order to reason causally, it allows for interventions and counterfactuals through the use of their replace function. So the omega object is essentially a retooling of this base RNG parameter in Julia. And for those who aren't familiar with Julia, this RNG is essentially a random number generator. But the problem with this is we can't track how this RNG parameter is passed through a program. And so what omega does through this omega object is it allows us to track where we are in the execution of a random variable. It essentially makes a random variable a pure function of its input. So if we pass in the same RNG value to a random variable twice, we should get the same value returned from the random variable. And then we have some code that shows how these are defined. And then we have the randvar object, which on the surface is a simple wrapper for a function. So say we had a function, a defined model that we want to turn into a random variable, we would just wrap that in the randvar object, and then we would have a random variable that could be executed. But when it interacts with the omega object, it essentially creates a pointer so we can actually track where in the execution this function is. Since it does produce that extra reproducibility, we can really go in and see how is this random variable getting executed based on that wrapped randvar function we have. And then again, we have some more code snippets in Julia and Omega to kind of highlight how this can happen.
Volterra is a pair of first-order nonlinear differential equations. These describe how a predator and prey interact with one another in an ecological or a biological system. The given equations, dx by dt and dy by dt, represent the rates of prey and predators respectively over time, where x is the number of preys and y is the number of predators. Alpha, beta, gamma, and delta are positive real constants here. We chose to work with this model due to its simplicity, and our implementation on this is a base case. And in theory, we can scale to any biological system governed by ODE or SDs. To simulate realness and mimic it, we use the Gillespie algorithm, which is the original stochastic modeling method, which employs random variable numbers to simulate individual reaction event and is thus a chemically exact method of simulating the dynamics of a biochemical system. It simulates random series of reactions just as they might occur in reality, which helps in capturing behavior that is lost in the less granular simulations. Each reaction has a probability associated with it, and the choice of next event is weighted by it. It has two random numbers, first for the time of next event and second to choose the next reaction. The result we get is similar to the ODE model, but we get additional information about the heterogeneity in the system, and these may not be apparent in the ODE model. Implementation details. Our implementation of Omega required multiple iterations, each building on the last one. We firstly implemented the Lotka-Volterra using Gillespie simulation, then converted the simulation to Omega. In Omega, we added random variable at each step to allow for conditioning and interventions. As Omega is a relatively new package and in Julia probabilistic programming language, it required us to work through some bugs and figure out how it works without having extensive examples given. We firstly did a straightforward implementation of Lotka-Volterra simulated using Gillespie. It allowed for testing of different discrete parameters. We tried different rates as well as different initial prey and predator values. In this, we couldn't do any causal questions, including conditioning or interventions. We can condition and intervene on any step at any time in the curve. We figured this out by taking the step as a random variable, which allows us to set a seed and run a counterfactual. Each random variable has the same initial conditions due to the same seed, which we define as RNG and omega. In the plots here, we can see that if we intervene on the initial prey value with the same set, there is one issue here that it requires a large amount of overhead with thousands of random variables in simulation, which takes a lot of time. We are trying to optimize this implementation, which we'll talk about in our next slide.
Progress, which shifts away from the usage of random variables at each time step. This allows us to intervene at varying time points because we don't have to keep track of significantly more and more random variables, which slows down the runtime of our program. However, as this is still in progress, we will be presenting our other model in our code review. In the Omega paper written by Zena Tavres, James Koppel, Xin Zhang, and Armando Soler-Lozama, they provide examples of using causal inference in an ODE model of the Locke-Volterra simulation. This is established the baseline of comparison, and we will be re-implementing this scenario using the Gillespie algorithm. As a subnote, direct comparison of our plots with theirs is not the most fruitful because they use the ODEs directly, and we use the Gillespie simulation of the ODE. This gives us different results, and it doesn't allow us to translate the usage of their parameters for this ODE to the parameters that we use in the Gillespie algorithm. And as we just found in our experimentation, even slight change in the parameters significantly change the output of the model. As the main difference, you'll notice there'll be very many artifacts throughout the plots, and it'll be significantly jumpier. This is due to the stochastic nature of the Gillespie algorithm. Here we show a basic simulation of our algorithm, which just shows nothing exciting here, just a single run with no change of the Locke-Volterra model. Here we show the conditional model simulation, where a conditional model is basically saying what would the simulation look like given that this happened. Here we have the statement that we conditioned on was that there were too many rabbits, which we translated to mean that the mean number of rabbits over the last 100 time points was actually greater than 40, which, as you can see in our simulation, is what occurs, where towards the end, the number of prey significantly jumps up in this iteration. An interventional statement asks the question of what would our statement look like had some value at some time point t been set to x. And here in our model, we intervene and say that we decrease the number of prey at t equals 250 to 10. And then we simply sample forward as normal using the Gillespie algorithm and continue. The treatment effect was determined to be the difference between taking this action and not taking this action. As you can see, at time equals 250, it might be a little bit hard to see because of all the jumpiness, but the number of prey gets lowered to 10 exactly, and then it continues forward. A counterfactual statement asks, given some state, how would our simulation have evolved differently had we made some other change? With the keyword here being given some state. In our simulation, what we say is, given a simulation where we observed that the mean number of rabbits to be 40 in the last 100 time points, how would it have evolved differently if we introduced 20 predators at t equals 250? Practically, this is essentially very similar to an intervention, but we fixed the random seed in omega. This actually showcases one of the main draws of using probabilistic programming for these kind of counterfactual questions, because it translates very intuitively in the terms of fixing the random seed to mean keeping the state the same. As you can see, we have at t equals 250 that the number of predators gets incremented by about 20, from about 60 to 80. And on the left, you can see the predator treatment effect, which is taking the difference as having done the counterfactual versus what would have happened had what would happen if the counterfactual not occurred. And as you would expect, the treatment effect is evaluated in the number of prey. And as you would have expected, it generally tends to be on the negative side, which means the number of prey actually decreases when you increase the predators, which is which intuitively what the Locke-Volterra model would say. This is simply just the first step of the overall goals of this project. The purpose of this project was just to develop the tools necessary to do counterfactual inference and ask causal questions. By utilizing the power of omega, what we can do is actually convert SPMLs that contain information about biological systems into causal models. And then, based on the results that we have done in our project, you can use the tools such as counterfactual inference, conditioning, intervening, to ask queries of a causal nature. So basically what we'll be able to do is convert any arbitrary SPML and ask any arbitrary causal inference query, and build upon these tools to construct larger and larger, more robust programs. Here are references used for our project. And now we'll move on towards the code review that we use to generate the plots.
The implementation of Omega and applying it to Lucca-Volterra was the main portion of our project. We wanted to be able to walk through the code, show how it works, and show some results. There are three main functions that go into this implementation. They are the getHazards function, one simulation pre, and one simulation pred. All three of these functions are used for one step of Gillespie. So first, the getHazard function takes into as parameters the RNG and N. RNG was mentioned as being integral to Omega in the slides, and N is just an index of the previous value in a list that keeps track of random variables. It first takes the pre list and pred list values, so those are the pre and the pred of the current step, and uses those to calculate the hazards, which are spawn pre to pred, and pred dies. Those are calculated with the rates defined at the beginning of the function, and those prey and predator values. Weights are then collected and used to calculate probabilities, and the categorical function from Omega is used to select one of those three hazards. Next, we have the one simulation pre and pred functions. These are both identical functions, but are used separately, so we can either intervene or condition on the prey and predators separately. So each one will take the hazards list, which is the result of this function up here, the previous value of the prey or the predators, depending on which function it is, and then it will apply a transition, which is a 2D matrix that applies how much the prey and pred should change based on the selected hazard. It'll apply that change and then enforce a positive integer so we don't zero out either of the values. There is one more important function to mention, and that's the generate rates function. Because our rates we specify as random variables, we want to only sample those once. We don't want to sample them at every step like we do for these functions. So those are sampled outside and then passed in to the hazards function here. So after we have those functions defined, the first step is to build the simulation. To do that, we initialize the parameters. This is the transition matrix specified that goes into the one simulation functions. And then we initialize the random variables for the starting points. So we initialize the prey, predator, and rates values, and then run that function I spoke about earlier. You'll see there's a couple different initializations for these, and these are just to either create bigger cycles or shorter, more compact cycles. And then we create a list of all of the random variables. So we're going to have thousands of random variables depending on how many steps you want to take. So just to get those all compiled here, we create lists for hazard, prey, and predator, push the initial values, indicate how many times we want to step through, and then for each of those steps, we compute a getHazards, a prey, and a predator random variable and push them to the initialized lists above. Each of these random variables will reference the previous random variable in the list in order to create their current values. The final thing we do here is to create a tuple of the random variables, which can be used to be passed to the rand function when we actually do the sampling. So moving on to the simulations now that we have the full function built, or the full implementation built. The first is just a simple simulation without any conditioning or interventions. So we set a random seed, we sample from the rand function, extract the prey and predator values from that sample, and plot them here. We can also do a conditional simulation. So in this case, because we want to condition over multiple values, we actually create the model a little bit differently. You'll see most of this is the same, where we create lists, how many times we want to run over in the cycle, and then go over each step. However, because we want to condition on prey for certain indices, if the step is in the conditional indices we want to apply it to, we will create the random variable and then immediately apply our conditional, and then append that conditioned random variable to the list. Otherwise, everything else goes through the same, and we can pass our created tuple to the random function. Again, extract the prey and predator values, and now you'll see for steps 1000 to 1250, these are all over 300. One note here, we are using rejection sampling, which can be dangerous if it's too restrictive. In that case, it may run forever, so there is an alternative, which is to use soft execution, which is built into Omega. Finally, we can run interventions or counterfactuals using this model. I'm going to recreate the initial model and run just the original simulation we had up above. So this is the same thing we had in the first simulation. Now, if we wanted to intervene on this simulation that we have, we can specify an index that we want to intervene on and use the replace function in Omega to set that to a new value. So we'll set the 15th index of prey to 300 and replace the original random variable with this intervened random variable here. Create our tuple, sample using the same random seed, and you'll see the intervention actually here, which takes the value for prey at time 15 and sets it to 300, and then lets the sample go through. You'll see since we use the same seed, it's a very similar simulation. And lastly, in order to show the treatment effect of this intervention, we can create a histogram and just run what I did here a bunch of times. So it's really the same thing. We set a new random seed for each run, do the samples, do our intervened samples, and then sum the prey values for the intervened samples minus the sum of all the prey values for the original sample, and then plot a histogram of them. And you can see when we do an increase prey at time 15 to 300, generally we see more prey than we would otherwise in the time period that we're looking at. And that is our implementation of Omega applied to the Lotka-Volterra algorithm using a Gillespie simulation. Thank you for your time. Bye.